Hello everyone. In this video, I want to share my experience completing an exciting assignment focused on advanced image generation techniques using ComfyUI workflows. The main goal was to transform interior spaces into various design styles using ComfyUI while preserving the original structural integrity of the given room. The design styles I worked with were minimalist, contemporary, Scandinavian, Indian traditional, and Japandi. Let's quickly break down the assignment. First, the assignment required collecting high-quality reference images for each of the 5 specified interior styles. Then I needed to select a provided interior room image and build a ControlNet workflow, specifically employing the ControlNet MLSD variant to maintain structural accuracy. Afterward, IP adapter workflow was to be utilized to apply each style to the original room. Finally, the task involved generating multiple images, showcasing the room transformed into each distinct style. Before diving into the workflow, it was essential to anticipate potential challenges that could arise during the process. Identifying these challenges in advance helped me take a more strategic approach and minimize errors along the way. A major issue I had to account for was the possibility of weak style application or mismatches between the generated output and the intended design. Additionally, there was the risk of structural integrity loss, where the room's layout could become distorted. Another challenge involved balancing the level of style adaptation, avoiding overfitting where the image would replicate the reference too closely or underfitting where the style influence would be too weak. Lastly, I had to be mindful of unwanted artifacts such as color shifts, unnatural textures, noise, inconsistent lighting, or unrealistic material rendering, which could degrade the overall quality of the final output. Now that we've clearly outlined the assignment's requirements and potential challenges, let's dive into the specific workflow required for this project in greater detail. The foundation of this workflow began with a basic text-to-image workflow, and then to ensure that the generated images retain the structural integrity of the original room, I incorporated ControlNet, specifically the MLSD variant. ControlNet played a crucial role in providing structural guidance, ensuring that important architectural elements such as walls, floors, and large furniture remained intact. The key nodes used for ControlNet workflow are Apply ControlNet node. This node plays a crucial role in determining how strictly ControlNet enforces the structural integrity of the original image. The strength parameter in this node defines how strongly the model follows the detected structural lines. A higher value enforces rigid adherence to the original layout, preserving architectural accuracy, whereas a lower value allows more flexibility, introducing minor variations in furniture placement and wall alignment. The start at and end at parameters respectively control when ControlNet begins and stops influencing the image during the diffusion process. Setting an earlier start ensures a strong structural foundation throughout, while a later end allows the model to introduce natural variations in finer details such as textures and decor elements, preventing the image from looking overly rigid or artificial. ControlNet preprocessor, MLSD lines. This node played a crucial role in detecting and preserving the straight-line structures of the original image, ensuring that the AI-generated output retained the key architectural elements. The score threshold parameter determined how strictly the model selected structural lines. A higher value filtered out weaker detections, keeping only the most confident lines and reducing unnecessary noise, while a lower value retained more details, including minor structural elements. The distance threshold controlled how closely detected lines were grouped together. A higher threshold resulted in broader, more generalized structural outlines by merging nearby lines, making it ideal for maintaining a clean architectural layout. Conversely, a lower threshold preserved intricate details, ensuring finer elements such as window frames and smaller furniture edges were accurately detected. Once the room's structure was secured, the next step was applying the specific design style using IP adapter. If ControlNet acted as the sketch of the design, IP adapter worked as the paintbrush, ensuring that the generated image reflected the chosen reference style. The key nodes of the IP adapter workflow are IP adapter unified loader is responsible for selecting the appropriate model preset, which dictates how strongly the reference style will be applied to the generated image. Once the unified loader is set, the IP adapter node refines the style application process further. The weight parameter in this node plays a crucial role in balancing style influence. A higher weight value enforces stronger adherence to the reference image's color palette, textures, and design elements, but it can also overpower the room's structural details, making it essential to find an optimal setting. On the other hand, a lower weight allows more flexibility, ensuring that the room structure remains intact while still incorporating the essence of the chosen style. Finding the right balance between structural fidelity and style accuracy required iterative adjustments and testing to achieve the best possible results. To further refine the image generation process and ensure better realism, texture quality, and adherence to the prompt, K-Sampler plays a crucial role. One of its key parameters, CFG, classifier-free guidance, controlled how closely the AI followed the textual prompt. A higher CFG value resulted in more rigid adherence, ensuring that the output matched the prompt more accurately, while a lower CFG encouraged more creative variations, allowing the AI to introduce unexpected but sometimes useful artistic interpretations. Another vital aspect of K-Sampler was denoise strength, which determined the extent of noise applied during the generation process. Lower values preserved more of the original structure and provided subtle refinements, whereas higher values allowed for more drastic transformations, potentially altering the initial layout. The steps parameter influenced the level of detail and refinement by increasing the number of iterations the model performed. More steps generally produced a clearer and more detailed image, but beyond a certain point, the improvements become negligible, leading to diminishing returns. Lastly, the sampler algorithm and scheduler dictated how the diffusion process unfolded, impacting the smoothness and realism of textures. Different samplers could subtly affect the final output, so selecting the right combination ensured better coherence in the generated images. The most crucial step was choosing the appropriate checkpoint model, as it directly influenced the overall quality, realism, and adaptability of the AI-generated outputs. The right checkpoint ensures a balance between structural preservation and stylistic flexibility. Since SDXL checkpoints were incompatible with ControlNet MLSD, I had to narrow my options to SD 1.5 checkpoints. After extensive testing, I found that different checkpoints varied significantly in their ability to integrate well with ControlNet and IP adapter. Some models excelled at generating photorealistic textures but struggled with structure preservation, while others maintained the layout but lacked strong stylistic fidelity. Through trial and error, I identified that SD 1.5, Realistic Vision 5.1 provided the best balance, ensuring both accurate structure retention and a high-quality style transfer. After gaining a clear understanding of the workflow and its critical components, I started applying them practically. However, as I worked hands-on, I quickly realized how overwhelming the process could be. Selecting the right checkpoints, adjusting image resolutions, and fine-tuning numerous parameters felt like an endless cycle of trial and error. Without a clear direction, I found myself making random tweaks, often leading to confusion rather than improvement. To overcome this, I realized that I needed a structured strategy. Instead of trying to perfect everything at once, an approach that proved inefficient and frustrating, I decided to break down my focus into key priority areas. This allowed me to systematically refine each element while maintaining flexibility for adjustments. By clearly defining these priorities, I was able to avoid endless tweaks and make more effective data-driven decisions. Structural accuracy. I placed structural accuracy at the top, focusing on maintaining the clear definition and straightness of walls, ceilings, and floors. Accurate placement of significant elements like beds, large windows, and curtains was also crucial. Elements such as minor furniture pieces and decorative items, while still important, were considered lower priority. Style transfer accuracy. For style transfer, I prioritized achieving a precise match of the color palette and overall tone from the reference image. Secondly, I focused on accurately replicating furniture styles and materials. Finally, smaller decorative elements and details, while contributing to authenticity, were ranked lower to ensure manageable adjustments. Quality and realism. Lastly, for quality and realism, my top priority was avoiding any visual artifacts that might distract from the authenticity of the image. Ensuring smooth, realistic textures on surfaces came next, followed by accurate lighting, shadows, and reflections. By clearly defining these priorities, decision-making became much simpler and more strategic. I could quickly resolve trade-offs by consulting my priority checklist, which provided clarity and significantly reduced stress during the parameter tweaking phase. This clear priority list simplified decision-making, especially during parameter trade-offs. Let me illustrate this with some practical examples to clarify how these decisions were guided by my priorities. Structural priority versus furniture. Details: when I increased the control net strength to achieve greater accuracy in the straightness of walls, ceilings, and floors, my highest structural priority, I noticed the furniture details, such as the style and intricacies of the bed frame and nightstands, became slightly less precise compared to the reference. Since structural accuracy was at the very top of my priority list, I chose to accept the slight compromise in furniture details. Color accuracy versus shadow realism. While aiming for a precise match of the color palette and tone, my highest priority in style transfer accuracy, I increased the IP adapter weight. Although this greatly improved the color accuracy, it introduced less realistic shadows and reflections, making the image appear slightly artificial. Given that matching the color palette was significantly more important to me, I accepted the minor loss in shadow realism. Clutter reduction versus artifact avoidance. In one scenario, reducing clutter by adjusting the prompt and lowering the denoise strength unintentionally increased visual artifacts, distortions, and unnatural textures, which contradicted my highest realism priority. Consequently, I reverted the adjustments, choosing a slightly more cluttered room image that maintained artifact-free, realistic textures and overall visual quality. By referring consistently to my structured priority list, these complex trade-off decisions became clearer and easier to manage. Having refined my approach through strategic parameter adjustments, I arrived at the final outputs for each design style. Here's a summary of what worked well and what didn't across all styles. What worked well. The final outputs demonstrated strong structural integrity, with walls, ceilings, and major furniture placements remaining consistent with the original input image. This ensured that the transformation into different styles did not compromise the layout of the room. Additionally, the core design elements of each style were effectively applied. The color palettes, furniture choices, and material finishes aligned well with the intended aesthetic, capturing the essence of each style without significant deviations. Another notable success was the realism in textures. Surface details such as wood grains, fabric textures, and material reflectivity appeared natural and visually convincing, enhancing the authenticity of the generated images. Challenges and limitations. While the generated images successfully retained the overall structure and applied the desired styles, some inconsistencies remained. Certain finer details, such as mirrors, nightstands, and decorative accents, were either missing or inaccurately positioned, leading to slight deviations from the reference images. Additionally, while the general aesthetic of each style was captured, some images struggled to fully reflect the intricate stylistic elements of the reference, particularly in the shape and detailing of furniture and decor placement. The challenge lay in maintaining a balance between structure and artistic influence without distorting essential design elements. Another challenge was managing visual artifacts and clutter. Some images contained unintended noise, excessive decor elements, or distortions that resulted from the trade-off between structural precision and seamless style transfer. Finding the right parameter balance was essential to ensuring high-quality, realistic outputs while preserving the intended room composition. Despite these challenges, the final results demonstrated a significant improvement over my initial outputs, proving that a structured and iterative approach to refining parameters is key to achieving better AI-generated designs. Through this assignment, I've learned that a structured, prioritized approach significantly simplifies complex workflows, allowing clearer decision-making and reducing overwhelm. Thanks for watching.